So good afternoon to everyone. Welcome to the 7 Galp Days edition. We have 4 rooms running in parallel, all with very interesting presentations, and you are free to move between rooms. At the end of each presentation, there will be a Q&A session. You can make questions during the presentation in the QA chat that you can find in the right side of your screen with a question mark icon. Also, to enlarge the streaming window, you should press the slide button. As chairperson of the session, we will have Elsa Azevedo Silva. Elsa Azevedo Silva is currently the head of geophysical methods within Geosolutions team at Galp ENP. She started working in the oil industry at Partex in 1996 and after passing through CGG joined Galp in November 1999. By the time, the company was restructuring its upstream sector and adding Brazil assets to the exciting Angola participation. During this time, she had several positions within the company, from technical roles to management responsibilities. At the present, leading a young team of geophysicists, she is responsible in Galp for seismic acquisition, processing, and for any non-seismic methods. Elsa holds a master's degree in geophysical science for the Faculty of Science of Lisbon University. Please welcome Elsa Azevedo Silva, and the floor is yours.
Thank you, Diana, for your introduction, and welcome to everyone for this section on subsurface. I hope that you'll hear very interesting talks this afternoon. So first, I would like to welcome Igor Bagno. Igor is a senior reservoir engineer currently at Primera Resources, working as consultant specialist in fracture carbonate reservoirs and characterization studies. He's graduated from Gapkin University in Moscow and EFP in Paris. He has a master in petroleum engineering and reservoir sciences and engineering. He started his career with the Gazprom project at a research institute in Russia and worked on a number of reservoir simulation projects for gas condensate and the fracture carbonate field development and monitoring. Continued his career with CFAL and Synergy in Russia and UK, worked on a number of field development projects, asset evaluation and reserves reporting. So today I welcome Igor to present a case study on fracture carbonate reservoir characterization from southern Apennines in Italy. So thank you, Igor and Paolo, and the floor is yours.
Thank you very much, Elsa. First of all, we'd like to thank Galp to organize this event. We're a traditional participant and very happy to present in this online edition. We are both speakers, myself and Paolo Pace from G.E.Plan Consulting SRL. We are partnering companies and we performed the current study together, and the case study is the project in South Apennines, Italy, and I'm giving the floor to Paolo Pace, who will present the geology part.
Thank you, Igor, for the introduction, and good afternoon to everyone. This study actually deals with a fractured carbonate reservoir, and this slide is actually willing to introduce a bit the concept of naturally fractured reservoirs. This is the Nelson classification of fractured reservoirs, in which essentially highlights the interaction between the two porosity and permeability systems that are actually characterizing those reservoirs. One is the pore perm system of the matrix, so the intrinsic reservoir properties, and the pore perm characteristics of the fracturing. In this specific case, we are dealing with a carbonate reservoir that has a floating fraction network developed, and essentially, these features are providing contribution to the storage and essentially the primary conduits for the flow. And basically, to assess the volumes in our reservoir and to predict this flow behavior that is primarily driven by the fracture network, we need to deal with both matrix and fracture characteristics, and they need to be carefully unraveled and integrated into the modeling. The considered case and presented case is a field redevelopment study. Field redevelopment has seen increasingly a number of small to mid-sized companies re-entering in mature areas onshore continental Europe, revisiting these mature fields and applying new technology to redevelop these abandoned fields. And the main challenge in these cases is that the reappraisal and redevelopment of those fields and discoveries to deal with the lack of information that is related to the vintage, usually old data set that is available. So we need to find alternative approaches to reevaluate and reinterpret those data. In terms of general Galp interest in exploration and development, it's worth it to highlight that this workflow that we adopt here is applicable from both exploration to appraisal and development cases. Here we are located in southern Italy, along the southern Apennines thrust belt, forming the backbone of the southern peninsular Italy. Here, the oil exploration is focusing at exploring compressional structure within the thrust belt that are targeting the so-called Apulian carbonate play. So it's hydrocarbons stored in compressionally deformed structures and dealing with a carbonate reservoir that is primarily related to carbonate platform deposits. This is the field that we examined in this study and is considered to be on trend on the well-known fields in the Val d'Agri and Temparossa, which are highly productive fields in continental Europe in fractured carbonate reservoirs. This slide is intended to show a summary of the Benevento field in southern Italy. This field was discovered on the early 70s, and it was appraised on a vertical well which tested light oil and gas, and then was put on production for 6 years. The trap is a structural trap, a pop-up structure, as can be seen from the interpretation of a 2D deep line that is related to deep-sea inversion tectonic processes. The reservoir section is basically constituted by upper Cretaceous to lower Miocene carbonates, and the top and lateral seals are represented by the 4 deep shales and maars that are present on top of the structure. The reservoir characteristics from core plaques reveal that the carbonate reservoir is very tight in matrix properties, so the fractures play a fundamental role. The reservoir properties from the matrix were analyzed in petrophysical terms, and the logs were upscaled to the reservoir grade. So this is an example of the upscaled matrix porosity and throughout the full field structure. That's a slide that is showing the general workflow that was adopted for the static modeling of the fault and fractures, from data analysis throughout the conceptual modeling, discrete fracture network modeling, and finally the upscaling of the fracture properties into the reservoir grid. Starting from the characterization and modeling of the large scale faults, so the fault and fractures that are at the seismic scale, 2D seismic was key to the interpretation of these faults, structural modeling for the definition of the general structure, and then outcrop analogs and the results of a strain model were essential in building the fault framework. In particular, the strain modeling that was aiming at modeling and simulating the structural development of the track during the geological time allowed to interpret the faults across the entire structure and to extrapolate the faults detected on 2D lines, both strike and dip lines, throughout the 3D space. Then the fault framework was modeled into the main structure of the field, and that represented one of the inputs of the DFN, whereas the modeled fault properties represented one of the drivers. The small to medium scale faults, so the fault and fractures at the reservoir scale, were characterized and detected from structural core logging, well logs that were available, the outcrop analog, and also here the strain modeling. Mostly the strain modeling and the outcrop analog were essential in defining the fracture sets, so the fracture populations, since borehole image logs were not available and the cores were neither oriented. The structural core logging was useful also to identify the fracture intensity, but their coverage was too limited across the reservoir section. So we found some relationships to the available well logs, deriving and computing the differential of the Young's module that was matching in trend with the fracture intensity detected from the cores, and this was then ultimately used as a driver and upscaled into the reservoir grid for as use based for the fracture intensity. The present day stress field was derived from basically literature data, GPS stress maps, seismotectonic models due to the active faulting that is present in the area to establish the fracture opening mode, fracturing mode at the reservoir level, and to evaluate qualitatively and constrain the fracture aperture to be used in the model. That is the conceptual model at the large scale that was built into the structure considering well data, the structure built from the seismic interpretation and strain modeling. At the medium wearable scale, we can distinguish the Cretaceous and Tertiary reservoir sections and some large-scale lineaments, and the distribution of the fracture intensity that was then upscaled into the model. At the small core scale, here we can better see the distribution of the different fractures that have been logged, the different types, as well as rubble zones related to small fracture, small faults, and the both tectonic and overburdened stylolites. And here we can see with more detail the relationship between the Young's module and the fracture intensity derived from the core structural core logging. At the end, different scenarios of fracture modeling were computed by combining the different inputs data from fracture sets, drivers for both background fractures and large-scale fractures. The wild sector models were built to establish the best fracture aperture permeability upscaling method and to calibrate the fracture permeability to the well tests, as Igor will show in a minute, whereas the full field model was upscaled for generating a dual porosity, dual permeability grid according to the different modeled scenarios. The overall conclusions from the static reservoir modeling perspective are the following. Actually, DFM models, so fracture models, can be built by carefully integrating all the available data and using alternative workflows. The wide ball scale and full field scales are useful for the DFM modeling. To establish aperture permeability upscaling methods, and then the fracture porosity and directional dependent permeability needs to be computed from the upscaled full field grids, and the best scenario was then selected after dynamic simulation. Now I'm leaving the scene to my colleague Igor Bagno, talking about the dynamic simulation.
Thank you, Paolo. Sorry for the few technical issues here for sharing my screen. I'll briefly cover the challenges that we had in our part of the study, which is the dynamic modeling part eventually. Benevento field is quite complex and from different points of view. First of all, as Paolo mentioned, this is a type 1 to type 2 reservoir in Nelson's classification, which means that the reservoir is tight and we need to take care accurately of the matrix fracture fluid exchange, and also model correctly the transition zone which is in the matrix, and provide the correct inputs to the volumetrics and the resource assessment. The second challenge we have is that the part of the reservoir is the significant part of the reservoir lies within the gas cap, and the gas cap is built of CO2, carbon dioxide, which has quite a high content in a gas condensate mixture. And the way we took that forward is that we modeled two cross sections in the wells area, Benevento 2 and Benevento 3, taking the input from the DFN and geological model and initializing the model such as that we model accurately the transition zone and the matrix fracture fluid exchange concepts. So the model is quite small, it's less than 100,000 cells. We have a dual porosity case, so that's doubled. And we had 3 cases depending on defined oil-water contact. So to model the transition zone, we relied on the Valdagri and Alocre, which is a neighboring field. So the capillary pressures were taken from there and scaled up to the residual saturations that we had from Benevento core plug. And we modeled the transition zone of up to 150 meters. So 100% water saturation at the free water level and 50% at the top. Briefly on the wettability concept, that is the example from the Val d'Agri, again, which is a neighboring field, proving that the wettability was mixed, means that it's not purely oil or purely water wet, it's oil wet in the fissures, in the microfractures, and water wet in the matrix itself. And on top of that, we reviewed the fluid compositions and fluid properties in both wells, and when we combine them, it is a section of 350 meters here, and the API of the oil varied from somewhere around 30 API to 39 at the lower part of the reservoir, and it was a gas condensate mixture of 45 API at the top, at the upper section. Field produced for 6 years. We history matched the production. Historically, the well was producing at a certain water cut, and then eventually the cone reached the bottom perforation, and the well started to produce more water, and eventually stopped producing because of the pressure. Then we matched all the successful production tests, which were about 10 hours long, and to validate basically the DFN permeabilities. And the final part of our study covered the CO2 miscibility, because the intention was to plan the reinjection of the carbon dioxide, and we had to analyze the miscibility of the pure CO2 or a separator gas mixture in order to keep the energy which we spent eventually on the separation, so without breaking the CO2 into keeping it in liquid state and rejecting into reservoir could be the viable option, but in this case we should keep a bit of methane in it. So we actually tested the pure CO2 and the separator gas mixture, and we modeled the slim tube tests, which proved that actually at the current reservoir and temperature, that is the viable option. And to conclude, the dynamic modeling part provided the key inputs for the STOIIP definition. We actually split the volumes which are stored in the matrix and which are stored in the fractures, accurately modeled the transition zone and the saturations, and then matched the DFN and calibrated it to model the development scenarios. And we'd like to thank our company client, and particularly Rafael Di Cuya and John Trine and Don Ferguson, for their permission to use the data for the study and for us to do the joint study together. This is the end of our presentation, and hope we'll have a little bit time for the questions. Thank you.
Thank you very much, Paul and Igor, for your presentation. I don't think we have any questions in the room. I can try to make one, although this is not the area of my specialty, but I can try one. You're having a reservoir with high content of CO2, I understood, and you are also injecting CO2, is that correct?
There are two options. It's the question of keeping the mixture in a liquid state, so keeping a bit of hydrocarbons in the mixture to keep it still keep it in a liquid state and then inject it as a liquid. Or we have another option, breaking the methane and all hydrocarbons from it, having pure CO2 but in a gas state. But then we need to recompress in a liquid. So we spend a little bit more energy on first of all separating it to have a pure CO2, and then compressing again to have it in a liquid state. So there was a question of keeping a little bit of methane in the mixture and inject together in a liquid. Yes.
Thank you very much for your participation and this challenging
Elsa.
field. Thank you.
Thank you very much. Thank you, Paolo.
Appreciate it. Thank you.
In a few minutes, we will have the next section. So we are waiting for the 4 o'clock. Just to remind you that at the end of each presentation, there will be a Q&A session. You can make questions during the presentation in the Q&A chat that you can find in the right side of your screen with the question mark icon. Also, to enlarge the streaming window, you should press the slide button. As a short person, we have Elsa Azevedo Silva.
Thank you, Diana. Let's wait then for the right time to start the next session.
Yeah, exactly.
You can see my screen just to check.
Yes, perfectly.
Okay, good.
Okay, thank you, Dag. I think we can start now. I'd like to give you welcome to Dag Helland-Hansen. Dag is currently the Global Exploration Advisor in EMGS and has 2 master's degrees, one in Petroleum Geophysics from Norwegian Institute of Technology and a master in Reservoir Evaluation and Management at Earthward. He has more than 23 years of experience in the upstream of oil and gas industry, and this is ranging from small to major oil companies and to services companies. So he has a broad experience in geoscience background with a specialty in quantitative seismic interpretation and the practical use of such data in geoscience interpretation and the hydrocarbon volumetrics and risk assessment. Currently is leading the Europe, Africa and Middle East business unit, while at the same time acting as the Global Exploration Advisor within EMGS. So thank you very much, Dag, for your participation again this year on these Galp Open Days sessions. And today you will share with us a presentation regarding technology development and modern use of CSEM. So, Dag, the stage is yours. Thank you very much once again.
Thank you very much, and good afternoon, ladies and gentlemen. As I said, last year I was presenting more of the technology development. This year I was planning to go a little bit more into the usage of CSEM. Sorry, I just need to find something. My mouse didn't work here. Just make sure that the technical. There we go. But I'll do a small introduction of what is CSEM, since it's not the everyday data set of every geophysicist like Seismic is. So a little bit about what it is, what it measures, and then a little bit of the development that has happened particularly the last 5 years, and then get more into how to use CSEM and some examples of how it's used worldwide. The classical use is really displayed in the figure to the right. You'll see that again. And it's all about highlighting which structures could be oil-filled versus which are not oil-filled. And it's all related to resistivity that the oil causes, that causes the electromagnetic signal to be different than in a brine-filled structure. We'll get more back into that. So if we go into the method itself, what we have is a vessel with a source that we tow along the seabed about 30 meters above. And before we tow, we have deployed receivers on the seabed that could be of a distance anywhere between 1 to 3 kilometers apart, depending on the target and what you want to illuminate. And then we send the electromagnetic signal from our source that goes into the subsurface, and that signal will change depending on the resistive nature of the subsurface. So typically hydrocarbons could be high resistive, while brine-filled shales are low resistive. And I'll show you a movie in a moment how that works. Then that comes up, and then we measure the signal in the receivers. And based on the receivers, we can see a change in resistivity along in the subsurface. And we have a processing and inversion process that transfers that to subsurface parameters. We have a number of sources actually, which are controlled source electromagnetics and of varying strengths. With these, we can tow with water depths from 10 and down to 4,000 meters. So more or less every target apart from transition zones. I don't think very many are drilling deeper than 4,000 meters. In addition, we can also use this EM field generated by the sun, which is called magnetotellurics. That gives us a very low frequency signal that could penetrate much deeper than the control source from electromagnetics. So with a towed source, we typically see are sensitive to targets between 0 and 4,500 meters below mudline. But with the MT sensitivity, we can see hundreds of kilometers into the subsurface, but that is typically for other purpose than oil and gas exploration. So this is how our setup looks like, and we'll get back to that model again. So this is us towing now a vessel across the seabed, and here is again this reservoir which is filled by oil down there. And then we emit the signal from the above here, and it propagates into the subsurface, and we'll be hitting these different layers. And as it, you will see as it hits the different layers, the velocity of that would change, and that depends on the resistivity. You'll see that as it hits this oil-filled reservoir, that the signal will shoot ahead and hit the end, and then it will transmit another signal going up to these receivers. So that's in this area, it's much smaller attenuation, and it's much faster. And so it propagates through there and hits there, and then the signal is recorded, and we can record enhanced magnitude and also reduce phase shift as you come across this layer here. So now the challenge is to get that signal up and display that in a fashion that is interpretable for geologists. So that would be the next phase. But before we get there, this actual signal that we see here, that will, similar to seismic and other geophysical measurements, have an area of investigation where it's more or less sensitive. And the parameters that varies with is, for CSEM, it's the net thickness times the resistivity delta, or the difference in resistivity over one body from the other one, times the thickness of that. That's one parameter that we're sensitive to. The other one is the area. So in the oil and gas case, the area of the prospect. The larger the area and the thicker the reservoir, the more sensitive we are to that prospect itself. The other important parameter is also depth. So we use this traffic light system, where in green we are sensitive and in red we are not sensitive to a specific target. and in this case it's depth versus area, and you'll see as we go down in depth, the area has to increase for us to see it. So at shallow depths, we can see very small targets with hydrocarbon accumulations, and at the deeper you get, the prospect needs to be larger and larger for us to be able to detect it. Then a lot of people would like to compare this with seismic, because seismic is the bread and butter of the oil industry. And just sort of give you an example how comparable or not comparable they are. So if you take the classical seismic wiggle display, this is your classical seismic data. But in order to improve that from seismic, we can go to, in this case, a relative acoustic impedance volume. Most geophysicists will be capable of interpreting here, but there is some improvements, and particularly for lithology of fluid, to go to impedance. With respect to CSEM data, the similar data will look something like this. And that is only for the expert to interpret. It's not easy for the geologist to interpret what this means. So for CSEM, we've also developed an inversion scheme, and it's a little bit, this is more a full waveform type of inversion, relative to the, this would be a post-stack amplitude inversion. But it gives you then a resistive volume in 3D. So this volume here would be comparable to your seismic. And most inversion or most interpretation work in CSEM happens on inversion products. But as with all inversions, they are non-unique, so we always need to take account for that there could be several solutions that explain the picture. However, CSEM has been used over the last, since about 2002, and it was a real hype around 2005 to 2007. And a lot of companies actually used it and drilled it, and they got a very mixed results out of that. And the reason for that is because the technology was very immature. So in the early stages, we were using this anomalous transfer move-out curves to detect where we had an anomalous resistivity in the subsurface. But you can only tell that it was somewhere in the subsurface, and you couldn't tell at which depth unless you tried to some modeling. So it's a very expert system, and it was very difficult to use. So from that sense, we developed a 3D inversion. However, this was our first generation, and it really wasn't good enough to be able to predict what we needed to predict. Only when we came to the second generation, this is over a field in the Barents Sea in Norway called Johan Castberg, and this is Equinor's data. We were starting to see now, call it a blob around that actual specific field. But what's really taken this forward is what we call now the 3D Gauss-Newton inversion that was developed in 2018 and launched. And this is the results we are now getting from the same data set. So you can see the improvement of how this field is outlining itself compared to only 3 years ago and then 10 years ago. And similar on the hardware side, this is an example from outside of Mauritania. And it's actually 3 reservoirs in here, and this will be your first generation hardware. We pick up this one and something faint here. Second generation would pick up this and something faint. And with the latest deep blue technology, we're really picking up everything in a proper sense. So the toolbox we now have, which we're also working with Galp on in Namibia to have a survey there next year as soon as possible that we can have the vessel down there, would be using this technology in combination with this technology. And that's when you're really getting the strength of this. So let's see how this works. So as I said earlier, it's a full waveform type inversion. And this is the model that we will arrive with. And in the early days, we needed to have a biased model, or call it a start model, to get close to this. That's what we don't need now. Our current start model is that we'll put in the seabed to just sort of get the sea correct. But below there's really half space of just a value. And we let the data drive the whole inversion process. And I will show you how this looks. So this is where we start. And then we measure the RMS data misfit as we get closer and closer to the real data. So this will be your first result, and you'll see the result coming down. Second, we move to here. And as we go along, we gradually improve on that, and you'll see that it stabilizes around here. And eventually we get the target which we're happy with when the misfit is 1. And you'll see in real time this was 28 iterations to get to this point. So that's the final model here. And for this one, we can then compare how does that compare with the wells. We have, this is the Tryon field in Mexico, and it's a discovery sitting right there. It's a stacked pay. We can only image the stacked pay as one accumulation, as opposed to seismic, which often can detect the differences. We can detect there is hydrocarbons here, but we can't really detect whether it's this reservoir or this reservoir. And then you have an appraisal well over here, and you see that be sitting at the very edge of this outline, which is in accordance with the operator's thoughts about the field. What you can also see is that our depthing is a little bit, it's not as good as in seismic, so sometimes we will miss the target in depth, and that's something you need to take account for when we interpret. Aerially wise, it's very well fitting, but depth wise, it's a little bit more of an issue. More so, as I said earlier, our signal and what we can detect also varies with depth. So actually in this well here, there is a deeper discovery, and this one we are not able to detect. And then you go back to this traffic light system, which shows this is the resistivity times thickness of the reservoir, which we call ATR. And for this target, it's very green. So this is the sensitivity threshold and the area. So we will be sitting out in the green for this reservoir. However, for this reservoir down here, which is significantly deeper, we will be sitting in the red to yellow area. Meaning that up front, we know we can only see this reservoir and we're not expecting to see that. And that's an important sort of modeling job to do prior to embarking on the survey to understand, can we actually image the survey? And we can do some imaging tests in addition to that, but I'm not covering that here. But rather on how to use CSEM. So in this case, we have a seismic cube, and we have defined some structures with some potential fills, or call them leads. So there's one here, it's another one there in the structural realm. And from seismic, the strength of seismic is really related to structures. You map out the traps, you can map the reservoir in certain cases, but to a lesser extent charge and seal. Obviously, you're looking for DHI, such as AVO anomalies or fluid contacts. But as we all know, that they can also be caused by only very small amounts of gas, so you never know. So this is where CSEM comes into play, is that it does not see a trap in reservoir. It sees actually the charge and seal because it's really seeing a hydrocarbon fill or not. And it can also indirectly calculate the volumes. So if you add CSEM on top of this seismic cube, you'll get something that looks like that. And what it actually does is that it high grades this lead here, so you can call it into a prospect, which increases the chance of success. And then it does not have an anomaly on this one, so it would actually decrease the chance of success on that one. But in this case, it actually saw another lead out here as well, which might be a strat trap that the seismic interpreter had not picked up from seismic. So you differentiate your portfolio by high grading or degrading prospects, and you can find additional prospects not identified before. So that's where you add the value and how that should be used in this type of case. Rather use of CSEM as well, and I'll get more into that. Then the question is, how well can we actually predict this? Particularly because there has been 10 years back, particularly a lot of mixed bag results, which mostly were related to poor inversion algorithms. So what we have done is to work with a number of super majors and done our own surveys based on this. So actually we've quantified more than 250 wells to see how well do we actually predict this. And what we have done is to sort of have a look at areas where you have a well and where you have CSEM results. So this is our try and discover again. and that's a clear anomaly, and it's a discovery. So that's an EM positive with a discovery. But then you have areas like this well out here, compared to this is a discovery down here, but in this case we're looking at this. Here you have in blue a very conductive series in shales, and this well is then dry, and it does not have an EM anomaly, so it's what we call EM negative and dry. So if you predict this, you're predicting it correct. If you predict dry well here, you're predicting it correct. But we do have cases where we have an EM anomaly that indicates hydrocarbons, but it could be something else. And in this case, this is mature source rock combined with some cemented sands, which is also resistive. It's just lithology related rather than fluid. So in this case, we'll call that an EM false positive, and it's where we cannot predict. In these cases, we're not able to predict the correct sense unless we use additional data like seismic. There are cases where you can understand that this anomaly is not related to fluids, but for the prediction strength, we're not using that. And then you have the other one, which is there's no EM response, but there is a discovery, and these are typically small discoveries because we are not sensitive down at below 1,000 meters to things smaller than 30 million barrels. And the false or the no EM response with discovery, we have a number of those, but they're all smaller than 30 million barrels. So that's something to be aware of. Very small accumulations we might not pick up, or very deep accumulations like the one down below Trion, we cannot pick up. But this is how we classify that. And then we have worked that up, and we did this with Total. So Total presented this at the SCG last year, and they came up in the wells we did together with them. That's 80% success rate in predicting either a discovery in EM positive or a dry well in EM negative. And then the EMGS continued that work. We also worked with other operators, but we did altogether in this case 250 wells, and we ended up with 82%, similar to Total's 80. And there are very few wells which are EM positive and dry, and then they have these ambiguous ones which are the discoveries, but they are very small. So they account for 13%, they account for 5%, but the majority you can actually predict results. And that this is also given that you work this in lithology, as we know it works. So we can't use this in the carbonates, and you can't use this for very deep, typical pre-salt fields. Then you would be able to predict the reserves like this. So coming then back to the conventional usage of CSEM, that is really as a fluid indicator. That's what has been historically what we've been using for, and what most people do, although I'll get into something that other people are doing it. And these are 3 case examples. So this is somewhere you could improve your chance of success in the portfolio. So this is from out far east, POR 1 and POR Ent1. So essentially, it's one discovery and a dry well. And essentially, obviously, this was drilled at that time. But using CSEM, you should be able to pick the prospects that work from those that does not work. Similar in the Barents Sea, very similar structures. This has residual hydrocarbons. It has all the fluid parameters from seismic, but it does not have an EM anomaly. Harvest, on the other side, had the same seismic features, but it has an EM anomaly. This is a discovery. This is a residual hydrocarbons. As well, this is shallow gas, but these are shallow fish gas, so these are the non-dangerous ones. I'll show an example of a shallow gas with proper saturation as well. So in addition to being used as a fluid indicator, you can also use CSEM to understand whether the shallow gas are saturated or not, and actually start to map out migration routes. Final example, this is the Xerolete field in Brazil. And this is the outline of the field. And as you go off structure, then you go into dry well here. This is an appraisal well. So this is the classical example. It's always preferable to use it on a portfolio because then you can differentiate one from the other one. And according to my understanding, that's what you were planning on doing in Namibia, which is a good way of using it. But then you get to this sort of finding additional leads. So this is what I call the hunting for the invisible strat trap. This is on this line here. This is actually a 600 million barrel field, and this is the field outline as it currently sits, and then the line goes in like that. And yes, you can argue that you can see something here, but it's not trivial on this monocline. But this is adding CCM on top of that. It makes it so much easier to figure out where you should be drilling rather than where you not should be drilling. So this is amazing results. And this is data actually from 2003. So the data in those days were good, but the processing in those times were poor. Then a little bit more ahead, this is Equinor. This is a prospect in the Barents. And the results from this was so good that we could actually quantify the amounts of hydrocarbons up front. What we actually had here was a structure, and this is outlining the seismic amplitude anomaly, and that was what Equinor was hoping for, was to fulfill. However, the CCM only had an anomaly in this reddish area, so much, much smaller than the seismic anomaly. And they drilled a well at the very edge. They were hoping to find gas or oil. They did find gas, but they didn't find any oil underneath. But the whole thing was used to actually quantify from our side and from the company I was working at the time, Aker BP. They used this, and they decided to not farm into this well because they were calculating the net pay in this area, and they saw it was much, much smaller than the commercial threshold in the area. So what actually happened then, if you're looking upon that on the chance of success or probability of success versus volume, was that we had a prospect sitting right there with a volume of X and a chance of success of X. The chance of success went up of finding hydrocarbons, but the volumes went down. And then Aker BP said, we'll drop this. Then coming back to the shallow gas versus high sat gas, this is a shallow field. This is called the Pion discovery in Norway. This is a field that it's shallow gas, but they're contemplating it for production, similar to fields being produced in the Netherlands. And this is how shallow, highly saturated gas and those drilling hazards would look like. They are very sensitive to CCM because they are very shallow. So what Equinor did then was to say that we have some gas prospects somewhere else. So this is one, and this is another one. And you can clearly see the top of the reservoir with a flat spot, top of the reservoir with a flat spot. So what they said was that this gas prospect could either be fish gas or it could be a saturated gas like in the Pion. So instead of drilling them, they acquired CCM, and they saw that these prospects here, which are very sensitive to CCM, were conductive and in blue colors, and this one is similar. They were needing to see something like this, so they dropped the license and said, we're not going to drill that. You can argue they should have drilled this, but this was too small to have any volumes. So this is what you call fish gas, and it's a good way of de-risking your portfolio without necessarily spending all the money to drill it.
Dag, just to let you know, less than 5 minutes now.
Okay, that sounds good. Then you have a company called OMV who has been pushing this even further ahead. So they've been using CCM on a field called the Wisting. It's the most northerly field in Norway. And they've been using it to actually map out the fluid fill in all of these fault blocks here. So here you can see on CSEM the clear how it defines that fault block and how this fault block has a deeper fill level. So it's quite amazing how you can actually map that out on a fault block level. So in order to get this, they actually acquired data which was denser than exploration data down to a kilometer. But it just shows the power of also this technology to do things which are similar to seismic. But in this case, the seismic is shown down here, and the anomalies from seismic are more, this is the gas tops, and they're more covered by that, while the oil is a little bit more tricky. So the CCM was their better bet, and they're now contemplating using this for 4D monitoring as well. Before I round off, we have a growing business actually for regional 2D CCM and MT. And essentially, we've been acquiring a number of kilometers, and a large part of our volume last year was 2D. And just two examples here. They're using it for basin modeling and petroleum system analysis, generating regional geologic models, and structural imaging. And sometimes they've been also using it to quantify structures on 2D and where to place your 3D seismic. So, before you invest in seismic to do 2D Cs, you have to figure out, is there resistive anomalies down there? So this is a case from that Chevron did some years back, and it was actually trying to map out the volcanics and base of volcanics, but seismic could never see a base of volcanics. And they also saw that there were sediments below the volcanics, and then they saw the basement underneath. So the image they got out of the CSEM combined with MT was significantly better than what you got from seismic alone here. And it's pretty amazing in my head what you can actually image out of CSEM and MT. And this is down to 12 kilometers here. So different usage, not for DHI, but certainly has its application. This is another one from the mid-Atlantic spreading ridge, and you're actually looking at the plume coming up towards the seabed here. So this is your mantle coming up, and this shows how it spreads. And this image actually goes down to 120 kilometers. We cut it at 50 here, and it was presented in Nature as an astonishing result. It just shows the power of using geophysics in a different sense. Furthermore, a couple of examples. This is salt imaging. And this case here is similar to this case. In the Barents Sea, some of the salt domes are connected to the mother salt, others are detached. And obviously, this can create different trapping scenarios than this can do. And what we found is that the CSEM combined with MT gives a very powerful imaging tool for salt, and that it's been very complementary where the seismic breaks down because of issues with velocity burden. Over to Brazil. Here it's used to map carbonates, so a high resistive carbonate. You can image that, and similarly here, there's a carbon. Yeah.
Sorry, we have just one question that we want to do before we end our time. Can we do it?
Yeah.
Okay. Elsa, you can go.
Yes, from our colleague G.E.Plan, and he was asking here, and congratulates you for the great presentation. First, asking if you were processing old data with the new routines. And two, you mentioned that MT penetrates much more deeply than CSEM. Can that technology be adapted to the use in the shallower sequences too?
To address the first one, yes, we are in. This is this data was acquired in 2003. And the data wasn't being able to use for anything, so we re-inverted it last year, and this was the result. So we are going back on a number of data, and we're showing very, very good results that we have internal. So yes, the question to that is yes, we're doing that, and we're seeing very good results from that. To address the final one, what we've seen on the MTCCM, actually, this one is the best case for that. The top part here is really from CCM, and the bottom part is from MT. Yes, you can use MT up in the shallow as well, but we don't get as good resolution because the frequencies are so low in the shallow section. So we do recommend doing both, but we have clients to do MT only also offshore.
Okay. Thank you very much, Dag, for your presentation. I think we ran out of time and we need to move on. So once again,
you see the conclusion just there.
Yeah. Okay.
Okay. Thank you.
Welcome.
Thank you, Dag. Now we can jump to Carine Roalkvam presentation. Don't forget that we have the Q&A session on the right side. Whenever you want, please just put your question on the chat, and then in the end of the session we will answer your questions. Thank you.
Okay, I'm not seeing Carine still.
Can you not see me?
Oh, okay,
it's
now
here.
I can.
Yeah.
Okay, very good. So welcome, Carine, once again. Carine Roalkvam is currently the Senior Support Geophysicist in PGS with more than 14 years of experience in oil and gas industry. Her core activity involves giving geophysical advice and support on acquisition and processing projects to commercial PGS teams and to clients. Prior to that, she took several positions offshore and onshore as geophysicist and project manager on a number of high technology projects. So thank you very much, Carine, for your presence today here. And you'll share today with us this presentation on innovative and targeted seismic acquisition and processing solutions for shallow to deep waters. So once again, thank you, and the stage is yours.
Thank you. So I hope you can see my presentation and hear me well. Yes, thank you for the invitation again. It's been a pleasure last year, and it would have been a pleasure to meet in person, but it's been really a really good presentation conference and I'm really happy to be part of it. So I will start with a PGS fleet update before moving on to the new technology and new solutions we've been working on, and introducing GeoStreamer X before I go a bit more in details and showing what we can use this technology for from shallow to deep water. So fleet update first. We now have 6 3D vessels in our fleet. 4 of them on the top here are the Ramform T-class. They all have an inventory of 16 by 8 kilometers of cables on board as a standard, but they can tow up to 20 cables. And we also have the Vanguard and the Sovereign with 12 and 10 streamers, 8 kilometers as a standard inventory. So you may have seen this slide before. I think I had it last year as well, but just as a reminder, so all our vessels are equipped with GeoStreamer, and GeoStreamer have been a game changer in the industry, introducing true broadband seismic. And what does that mean? It means that there is several advantages. With the dual component, we can tow deeper without compromising the bandwidth, and with that reducing the noise level. We also have an effective sea surface removal, and if we combine all of the above, a high resolution data set. If we combine GeoStreamer with the leading source and streamer steering gist that we have on our vessels, this gives really high 4D repeatability. In the last few months, even in really tough time for different reasons, as you know, the fleet have shown their expertise, and we've got several records that I wanted to talk about. Ramform Atlas was working a really harsh operational area with really strong currents, and even with that, they actually beat the production record, so the efficiency was excellent during the full survey. Ramform Titan in Brazil had the largest streamer spread ever. We did it before, but it's still record with 14 by 10 kilometers streamer spread in the water. And Ramform Vanguard in Europe for the second year in a row had the widest ever source separation towed by a single streamer vessel on a commercial project. I will come back to that one a bit later on. So last year, I presented the results on our what we call the 2-in-1 solution, which is a variable streamer lens configuration that has long tails for full waveform imaging, full waveform inversion velocity model building, as well as dense cable configuration for high resolutions. Since last year, we've built on this configuration and applied it in other areas. We've done another commercial project in Norway with the Vanguard last year, and I've done two projects with long tails this year in Norway as well, with 2 to 3 tails at 10 kilometers, when the rest of the streamers are about 7 to 8 kilometers. We've also done a lot of long offsets acquisition. You can see here the one mentioned before with the Ramform Titan with 14 by 10 kilometers, and in that case that's the full spread as the same lens. What we've been working on is a way to get the near offset sampling. So in order to get accurate AVO analysis, especially in shallow targets, we need the near offset sampling. So the near offset coverage is defined by the green arrow here, but you have different ways of reducing this green arrow. You can reduce the saline separation shown by this red arrow here, but this is also controlling the cost. So if you do reduce the saline separation, you increase the cost of your survey, which is not really something we want especially in a difficult market. So in order to improve the near offset sampling without compromising the efficiency or the cost, we can also tow the sources wider, which is shown by the black gray line here. So of course this is not that easy. It comes at operational challenges, and which is why we've not really done it in the past. But we've been working on this solution the last year, really, since early 2019, and got really good results. So the drawn picture to the right here is the almost finished survey in Viking Graben. They're supposed to finish tomorrow, and you can see that they towed a triple source with 250 meter total source separation. So every source were 125 meter apart, and this is towed by the same vessel as the cables. This is the recent track record on wide tow sources. So you can see that we've been a bit busy and gaining experience with wide source since 2019. So the first project was in Australia with a dual source with a total source separation of 112.5 meter. We've then moved on to a Norwegian survey with the Vanguard with 225 meter wide source. I will show some examples later on. And this year we did the extension of the survey and managed to tow 250 meter. With the building the experience, making sure that we find the right solution to have stable sources, but also finding the right solution to tow the sources. We're now confident we can go as wide as 300 meters with single string sources, so for quad or penta sources. So building on our experience in multi-azimut, but also using all the different solutions we've been developing the last few years, we decided to combine it all and redefine multi-azimut solution to create an innovative and cost-effective single vessel multi-azimut acquisition. And this is what we call GeoStreamer X. So what is GeoStreamer X? GeoStreamer X is a flexible solution to address today's exploration challenges, and it includes dense spatial sampling for high resolution, wide to multi-source acquisition for optimal near offset sampling, AVO and shallow imaging, long offsets for full waveform inversion velocity model building, multi-azimut for improved illumination, but is also using the deep tow geostreamer for best signal-noise ratio, and the significant efficiency gain and reduced environmental footprint. That's if we compare to a multi-vessel survey or OBN. So we've done a pilot in Norway in 2019. And I will show some more examples now. So we did a survey in an area where we already had some vintage survey, and the challenges in the area are some sand injectites, what we call V-brights, that are causing imaging shadows, and as well as the thin chalk layers that is introducing a lot of noise. We did some survey modeling and concluded that we needed to deploy wide-tow triple source, close to zero offset, with a total source separation of 225 meters. We had 12 streamers with a corresponding streamer separation of 84.375 meters. That is just what we did need for the 225 meters source separation. And that gave the optimal near offset distribution. In addition, we have deployed two long tails of 10 kilometers for the optimal full waveform inversion velocity model building at target. And we added two additional azimuth on top of the one legacy geostreamer survey we had in the area. So these plots are actual CMP coverage plots. The legacy data to the left and the azimuth 1 on the new acquisition to the right. The black outline is the outline of the survey, and the blue is the actual coverage achieved in both surveys for the 0 to 125 meter offset range. As you can see, the azimuth 1 is almost completely covered, while the near offsets in the legacy data is not useful, is too sparse. One of the success criteria for the GeoStreamer X pilot was to populate these ultra near offsets, the 100 meters in line offset, with sufficient data points to be used in imaging, but without compromising the cost of the survey. And that was achieved with the wide source. What we try to achieve when we do the survey modeling is see what we need to get a 3 degrees angle for the amplitude analysis at target. So how does that look on some stack? This is a seismic section. So the little square here shows an inline. So yeah, that is the fast track for the GeoStreamer X to the right, and an equivalent fast track of the legacy data to the left. So you can see how the seabed and shallow sections are healed in the geostreamer X seismic sections. You can also see the contribution from the white source on the time slice. The time slices are about 200 milliseconds. So to the left, the legacy again, and to the right, the Mars early out PSDM for the geostreamer X. And you can see that we almost completely removed the acquisition footprint. So the imaging of the water bottom, the very shallow, was not really crucial for this area because the targets are a bit deeper, but it still shows the potential for shallow targets in other areas such as Barents Sea or even some areas in Asia and close to the shallow areas in Africa, for example. So why the loss? To the left, you can see an image of a bird eye view of the acquisition setup. The short blue lines are the 6 kilometers streamers, and the long blue lines are the 10 kilometer streamers on the 2 new azimuths only. The image to the right shows what offsets are required to record the diving waves at various depths in the area. So this is using our modeling from the vintage data. So the 6 kilometer offsets diving waves is going a bit shallow, while the targets in this area are below the sand inject tides, the V bright. So you do see that you need the 10 kilometers offset, to have a good velocity model update. Here you can see a depth slice to the left and a cross section to the right from the current stage velocity model building, and the respective red lines show the intersections. So both illustrates well the good correlation in the velocity model and the seismic after the full waveform for using the 10 kilometers offset. So you can see this blue low velocities localized sand mounds and the very high velocity contrast of the sand injectides. Really well correlated between the seismic and the velocity. The background model is also showing excellent correlation with available well data. And this is all done with data-driven with the full waveform inversion. We are about to finalize the velocity model building. It is adding some more resolution down to chalk or bit of basement in the area. So the full waveform inversion modeling we did to understand what kind of offset we needed for the cables were consistent with what we see on the real data. So this is just a regional line showing the fast track results and an early result of the velocity model building. And I think you can agree that we can see really high potential in the data. There is really high resolutions. The V brights and the sand mounds are quite high resolution, and for those who know the area, the chalk is normally introducing a lot of migration noise in the area, but with the multi-azimuth and the dense resolution, we do get a better signal-to-noise ratio in that area. So just to summarize, this was GeoStreamer X for shallow water. But again, this is a very flexible solution. And I will move on to deep water, showing some concept we've been working on in Brazil. So one of the main focus in Brazil is the ultra long offsets because of the deep targets and in the area. So deep targets, deep water. So the tails we know are not long enough. So this is just an illustration showing an additional vessel to the front to get the ultra long offset. So last year I presented the results of our reprocessing in the Santos Basin. We've done a reprocessing of more than 4,000 square kilometers of seismic data, getting a seamless and accurate regional pre-salt imaging. And we've based on our experience in the area and the results we got, we did create a model, some interpretation to base our survey modeling on. And this is a cross-section showing some of the interpretation we had in the area in the study. So what we did with it is then to do a full waveform inversion feasibility study to understand what kind of lens we needed to get a proper velocity update down to pre-salt, down to target. So in that case here, you can see that the 8 kilometers offset will not be enough to get an update down to pre-salt, which is around here. But when I move on to 20 kilometers offset, you can see that we do get a good velocity update down to pre-salt, and so we need to find a way to get this 20 kilometer offset. So there is different way of achieving this ultra long offset. What we call the SLO is well known. We had one source vessel in front of the main vessel, which in that cartoon here will give a maximum offset of 20 kilometers. But this is a known way of doing it. It works, but it might not be the best solution for areas like Brazil, where we have environmental restrictions. So what we've been working on is a solution where we don't add source, but we add cables. So in that case here, we had a second vessel, towing only other cables, additional cables, back the main vessel, in order to get the 20 kilometers offset. So this vessel can tow a number of cables, 3 or 4 cables, depending on the configuration we do choose. I've now presented 2 solutions, 2 different areas, from shallow to deep water. Again, this concept is not restricted to those 2 areas. It can be adapted to any challenges we may have. And this is another example where we actually looking at a few options. It's an Angola mega survey, and you can see regional horizons interpreted and the location of some of the known fields in the area. We also highlighted some remaining opportunities, and we can use the mega survey to find out these opportunities and find new prospective features in pre-salt, but in order to unlock the remaining potential, we need new data, and that's what I wanted to bring today. Is that the solution we have is a flexible solution that we need to understand challenges in order to find the right solution for using the flexible acquisition and processing solution we have in-house.
Okay, thank you, Carine. Just to let you know, 4 minutes now. Oh.
Yes, and it's perfect because it's finished. So thank you again for inviting me. And if you have any questions, I'm feel free to ask or contact me later on.
Yes, so I think we have. So thank you very much for your presentation. We have one from one of our geophysicists that thank you for the excellent presentation. And his comment, considering the low value on the oil price nowadays and the companies trying to reduce costs and maximize the recovery factor, in fields already with a high production, he wants to know how PGS is working on the logistics of operating with long offset cables and multi-azimuth in areas with many obstructions, and what would be the impact on the quality of the seismic data? Carlos is doing this question.
Yeah, so when it comes to obstructions in the area, I would say it depends what you want to achieve, right? I'm not sure if that we will never be as good as nodes for that, but we can do undershoot. We can walk around. Walking around obstructions is nothing new. Multi-azimuth or not multi-azimuth, we do it every day. We've almost complete a project in North Sea again without any HEC incident, nothing happening, excellent communication between platforms and us, and it worked really well. And we do achieve really good results there. So we have a limitation as how close to obstructions we can get. We still have a lot of cables and to take care of, yes. But it doesn't change.
This idea of increasing the offset to 20 kilometers as you shown on the last slides is still an idea, or you already tried to put that in practice with the second vessel just with cable?
So this one, for example, we have not acquired a commercial survey with it. We have de-risked it in-house. To be honest, we've done one cable, a multi-vessel acquisition before, and we have experience in-house. We do not see any major challenges in it. We're quite confident we can achieve it, but we have not done it commercially.
Okay. And how does this compare with the other methodology of having on the same vessel longer cables?
So the only problem with the tails in that respect is that the cables can only be 10 kilometers length. That is the maximum we can achieve, and that is not enough in Brazil or any areas with deep water and deep target. Yeah. So when we do see that we need more, then we need a multi-vessel operation.
Yeah, understood. Thank you very much, Carine, for your presentation and your good ideas put here in place. Thank you for sharing that with us. And I think now we can end this session. And if the other participants are still there, thank you for all the presentations that you shared today with us, and please keep safe.
Thank you again.
Thank you. Thanks, Carine. So we have finished the second day of presentations into the room 3 of the 7th Galp Open Day. We would like to thank you all for attending the event. Thank you, Elsa, for your collaboration, and also the speakers for the very interesting presentations. It will be a pleasure to have you here tomorrow at 2 p.m. on room 1 for the debate Economic Impact and Outlook on Oil and Gas Sector. Thank you all once again, and keep safe.